Hello and welcome. In this video, we'll solve few more problems on types of relations. So let's start with problem number 1. We have a set of all real numbers. So S is a set of all real numbers. So S is set of all real numbers. So real numbers means it involves all numbers like from minus infinity to plus infinity. Like we have whole numbers, fractions, and irrational numbers like root 7 and so on, negative numbers, negative fractions, negative, negative, irrational numbers, and so on. All these numbers we have in the set of S. And there is a relation which is defined on this set such that we have to take two numbers a comma b such that it satisfies this condition where a square plus b square should be equal to 1, and a and b belongs to set S, that is set of real numbers. And we need to check which properties this relation satisfy. We'll start with reflexive property first. So we know that every element in the set, should be mapped to itself uh, to say the relation is reflexive. Let us take any one example. If I take 0, so if I pair 0 with 0, so does it satisfy this condition? So 0 square plus 0 square is 0, which is not equal to 1, which is not equal to 1. So 0 comma 0, 0 comma 0 cannot be a member of this relation. So you cannot put 0 comma 0 here because 0 comma 0 does not satisfy this condition. So even one element cannot be paired itself, and this is enough for us to say it is not reflexive. It is not reflexive. Let us check for the second property, which is symmetric property. For symmetric property, we know that for every a comma b, which is a member of R, if b comma a is also a member of R, then it is symmetric. So any element which is satisfying this condition, like let's say 0 comma 1, which satisfies this condition because 0 square plus 1 square is 1, and the reverse of this, which is 1 comma 0, it also satisfies this condition, 1 square plus 0 square, which is 1. So this is also a member of R. So for every what I'm trying to say is, for every a comma b which satisfies a square plus b square is equal to 1, then b comma a should also satisfy this condition because b comma a is b square plus a square. So we are just interchanging the position of these two elements, but that does not alter the sum, which is 1. So any ordered pair which satisfies this condition, any ordered pair a comma b which satisfies this condition, b comma a should also satisfy this condition. So it is clearly symmetric. It is symmetric. Now let us check for the other property, which is transitivity. Transitive property. Transitive. So it says a comma b, and if a comma b and b comma c is a member of R, then a comma c should also be a member of R. So these type of relations are usually not transitive. So we can take one counterexample to disprove this. So let us take a is equal to 1 and b is equal to 0. So this satisfies this condition because 1 square plus 0 square is 1. So a comma b or 1 comma 0 is a member of R. Now I'll take b comma c as 0 comma 1, b comma c 0 comma, because 0 square plus 1 square is 1. So 0 comma 1 is a member of R. So this is my b comma c. Now let us check whether a comma c is a member of R or not. A is 1, C is also 1 from these two conditions. So 1 square plus 1 square is actually 2. This is not equal to 1. So this cannot be a member of R. So this one example is enough for us to say it is not it is not transitive. Not transitive. So the only option is it is only symmetric. So option A says it is symmetric but neither reflexive nor transitive. Let's move on to the next problem. Here we have a relation R is equal to x comma y, and the condition is x square plus y square should be less than or equal to 4, less than or equal to 4, where x and y belongs to I. So I is actually integers, set of integers, or we can denote it by letter z. So now what we have is we have set s is equal to all the integers 0, 1, 2, 3, so on up to plus infinity, and we have -1, -2, -3 towards the left side. So this is my set. Now I have to pair two elements. I have to pick two elements from this set and pair it like this, which satisfies this condition: x square plus y square is less than 4. So let us check for reflexive property. We will check for reflexive. Check for reflexive. So let us pair 3 with 3. So 3 with 3 is 3 square plus 3 square, which is 9 plus 9, which is equal to 18. So which is not less than or equal to 4. So 3 cannot be paired with 3. And there are so many elements where we cannot pair to itself. So in reflexive property, every element of the set should be paired to itself. So this clearly says it is not reflexive. You can take any example if you want. Next we'll check for symmetric. So here, if any two elements, let's say a comma b, which satisfies this condition, a square plus b square less than or equal to 4. So we actually select this pair of elements such that these two elements satisfies this condition. So if this is a member of R, then b comma a should also satisfy this condition, because when you give the input as b comma a, the output is b square plus a square. So we are just interchanging the position of these two elements, but this will not change the outcome, so which is less than or equal to 4. For example, if I take 0 and 1, so 0 square plus 1 square is 1, which is less than or equal to 4. And if I reverse it, 1 comma 0, so it is 1 square plus 0 square. So just I'm interchanging these two. Since the square and addition will not change the outcome of the function. So here we'll get 1 less than or equal to 4 only. So if a comma b is a member of R, b comma a is also a member of R. Hence it is symmetric. It is symmetric. Now rub this to check for transitivity. So usually these type of functions are not transitive. So we can take one counter example. Transitive. Let's take a comma b as 2 comma 0, b comma c as. For this type of examples, you always take one of the elements as 0. That will help to counter it. So I'll take b comma c as 0 comma 2. Then I have to take a comma c as 2 comma 2. So here 2 square plus 0 square is 4, which is less than or equal to 4. So this is 2 comma 0 is a member of R. 0 comma 2 is also a member of R, because 0 plus 4 is 4, which is less than or equal to 4. So 0 comma 2 is also a member of R. Now if these two are the member of R, then 2 comma 2 also should be a member of R. if we want to say this satisfies the transitive property. But here it is 2 square plus 2 square is 8, which is not less than or equal to 4. So 2 comma 2 is not a member of R. So this says it is not transitive, not transitive. So it is only symmetric. Let's move on to the next problem. Okay, we have here the set is natural number, x is natural number, so s, or we can take this as, let's take the set s is equal to, the element is natural number and it is less than or equal to 5. So what we can do is we can write all the numbers clearly here, 1 2 3 4 and 5. This is my set because every element of the set is a natural number and it is less than or equal to 5. The relation is developed like this, which is 1 plus x and 1 plus x square. So if x is equal to 1, I get first element, first ordered pair as 1 plus 1 2 and 1 plus 1 square. So 1 plus 1 square is 1 plus 1 2 again. So it is 2 comma 2. Next we have 1 plus 2 is 3. If x is equal to 2, we get 1 plus 2 is 3 and 1 plus 2 square is 4, which is 5, 3 comma 5. Next I'll take x as 3. If x is equal to 3, I'll get 1 plus 3 as 4. 1 plus 3 square, 1 plus 9 is 10. Next I'll take 4. 1 plus 4 is 5. 1 plus 4 square, 1 plus 16 is 17. And finally we have 5. 1 plus 5 is 6. 1 plus 5 square, 1 plus 25 is 26. So now we'll check for all the properties. That is reflexive. Clearly it is not reflexive because only 2 is paired to itself. All the other elements 1, 3, 4, 5 are not paired to itself, so it is not reflexive. We'll check for symmetric property. It's clearly not symmetric because we have, if you take 3 comma 5, 3 comma 5 is a member of R, but 5 comma 3 is not a member of R, so it is not symmetric. Not symmetric. Let us check for transitivity. For transitivity, so let us take this example 3 comma 5. 2 comma 2 is self transitive, that we know. We'll check the next pair, which is 3 comma 5. 3 comma 5 is a member of R. Now I'll check any ordered pair which starts with 5. There is an ordered pair which is 5 comma 17. 5 comma 17. 5 comma 17 is a member of R. But 3 comma 17, which is, this is A comma B, this is B comma C, this is A comma C. This is not a member of R. We don't have 3 comma 17. So it is it is not transitive as well. So it is none of these. So next problem. So here we have again set of natural numbers. S is equal to set of natural numbers, but x is less than 4. We can write 1, 2 and 3. The relation is x comma y is taken such that y is x plus 5. So let us take, if x is equal to 1, y is 1 plus 5, which is 6. If x is equal to 2, y is 2 plus 5, 7. If x is equal to 3, y is 3 plus 5, 8. So only three ordered pairs. Let us check for reflexivity, symmetric and transitive properties. It's not reflexive, because 1 1 2 2 3 3, all these are not present, not a member of R. Next we'll check for symmetric property. Symmetric property, it's not symmetric because 1 comma 6 is there in the relation, but 6 comma 1 is not in the relation, so it is not symmetric. Let's check for transitive. For transitive, let us check for first element 1 comma 6. 1 comma 6 is a member of R. 1 comma 6 is a member of R. I have to check whether any ordered pair starts with 6 or not. There is no ordered pair which starts with 6. It is not R. So it is enough mm, to say this satisfies transitivity, first element. So we'll check for second element. 2 comma 7 is a member of R, but there are no elements which starts with 7, so this is not a member of R. Similarly, we have 3 comma 8, which is a member of R. There are no ordered pair which starts with 8, so is not a member of R. So we know that to say any relation transitive, we should check the presence of both a comma b and b comma c. If these two both are member of R, then if a comma c is a member of R, then it is transitive. If a comma c is not a member of R, then it is not transitive. But here we are not getting b comma c only. We have only a comma b. So it is transitive. So it is transitive. We have already discussed this in the previous videos clearly. You can refer to that videos. So it is only transitive. Now let us move on to the next problem. This is an interesting problem. The nav set is all real numbers from minus infinity to plus infinity, which contains whole numbers, rational numbers, fractions, negative numbers, negative roots, negative fractions, etc. All these numbers we have in the set of relations. Now we have to develop a relation. We have to develop a relation on this set such that 1 plus AB is greater than 0. So let us check for reflexive property. The reflexive property will check. So here, let us take any element. See, when for reflexive property, what we have to do is, can we pair every element to itself? If I do -1 and -1, if I pair this, so 1 plus AB. So here A is -1, A equals B, and B is also -1. So 1 -1 -1, you'll get 1 plus 1, which is greater than 0. So -1 comma 1 is a member of R. So, or in generally what we can write is, so we have 1 plus AB. So if I pair every element to itself, then it becomes A comma A. It becomes 1 plus A square. So here we have plus positive. A square is always positive. So if I add 1 to any positive number, 1 plus to any positive number, the result is always positive. So result is always greater than 0. So you can pair every element of this real number to itself, which satisfies this condition. So obviously this is reflexive. This is reflexive. So 1 plus a square is always greater than 0. So this is reflexive. This is reflexive. Next, check for symmetric property. Symmetric property, we have 1 plus ab for a comma b belonging to R, 1 plus ab greater than 0. So for every ordered pair which satisfies this condition, 1 plus ab, let's take 0 comma 1. So this satisfies this condition because 1 plus 0 is greater than 0. Now if I interchange this 1 comma 0, then I'll get 1 comma 1 plus 1 into 0. So just by interchanging these two elements in the product does not alter the product itself. So this is also greater than 0. So what I mean is, if I have a pair a comma b, which is a member of R, means it satisfies 1 plus ab greater than 0. Then if I interchange these two elements b comma a, 1 plus, so this has to be a member of R. So if I do what b into a, if this is greater than 0, this also has to be greater than 0, because we are only interchanging the elements in the product. So this has to be a member of R. So this is symmetric as well. This is symmetric. This is symmetric. Now let us check for transitivity. So usually these type of relations are not transitive. So we need only one counterexample to prove this. So what we do is, so here we have 1 plus ab greater than 0. So 1 plus AB should be greater than 0. It means positive. So what I do is I always take one of the element as 0. I'll take this as 2, this is 0, and I'll take and C as B and C as 0 and minus 3, and and I'll take as A comma C. I have to take as 2 comma minus 3. So A into B is 1 plus 2 into 0, which is 1, which is greater than 0. So 2 comma 0 is a member of R. I can take this as a member of R. Here 0 into minus 3. So 1 plus 0 into minus 3, which is 1, 1 plus 0, which is 1, which is greater than 0. So 0 comma minus 3 is also a member of R, also a member of R. Now we have to check whether 2 comma minus 3 is a member of R, not R or not. 1 plus 2 into minus 3, so which is 1 comma minus 6, which is 5. 5 is not greater than 0, it is a negative number. So 2 comma minus 3 is not a member of R. So this is not transitive. This check for transitivity. This is not transitive. So I think option A is correct because it is reflexive and symmetric but not transitive. We'll solve few more problems in the next video. Thank you.